Why not? Matter of style. I think if you want to use fixed point everywhere, nobody will object. It's adding a little bit of extra information to the person that's reading the code that says you don't need to bother looking for the recursive occurrence of this. Maybe it's a little bit OCaml versus Haskell style. So in Haskell, everything is naturally recursive. And in OCaml, things are not recursive unless you explicitly say. So I think that distinction percolated into, or was inherited by coq. Other questions? Okay. All right. Let's ask you some questions. So do not submit any response when you have the answer. Raise your hand when you have the answer to this question in your mind. How many hands are up? A few hands going up. Okay, I'll give you another couple of seconds. Doesn't matter if you're wrong. Okay, many hands are up. Who wants to say? Too many hands up. You say.
Okay, does this like take the list and then append to that the list or the tail of that list and so on and so forth?
Ish. Let's try again.
So if you give a number, then it gives you a list back from 0 to n-1.
Yeah. So you give it a number. You can see that you give it a number from the first line, and it's going to give you back a list of numbers, and that list will contain the numbers 0 to n-1.
I think so.
N to 1. In which order?
Descending.
Descending. So we'll have n at the front and then n-1 and so on, but it won't have 0 at the end because we returned nil here rather than a singleton 0 list.
Yes, but if you call it with 1, if you put a 0,
Let's check. If you call it with 1, what will you get back? A list containing just 1.
And a 0. A 0. Because 1 is S0, and if you put the 0 in front of 0.
I don't think so. Okay, so if you call it with 1, what will happen? Let's work it through.
Okay, sorry.
Yeah, so you give it n, it matches n. So you give it 1, pattern matches 1, 1 is successor of 0. So it puts 1, cons foo of 0.
Okay, so 1 to 1.
And foo of 0 is nil.
Okay, sorry.
No need to apologize. Being participating and getting it wrong is better than not playing. Okay, so all of this is reasoning about lists. All of this is defining programs using lists. Now we want to reason about those programs. And what tactics do we need? Well, all of the ones that we've already used are useful. In particular, for properly recursive definitions about lists, we will want induction. Okay, so sometimes you can do proofs about lists just using simplification if the thing you're proving is particularly trivial. Sometimes you need case analysis that you can get just using destruct. But mostly you need induction. So here, for example, is the associative property for the append function, and we prove it by induction on what? Well, we have 3 lists here, so in principle there are 3 things we could do induction on. How do we know which one to use?
The definition of the function and see on which one it calls it here?
Indeed. So the smart answer is we look at the definition of the function and we see on which argument is it making a recursive call. The less smart answer, which is the one that I might give if it were late at night and I were in the middle of hacking on this, is try it and see. And in general, the smart answer may require arbitrary amounts of smartness. So The main difficulty, in fact, in doing many proofs in coq, as in any other kind of proofs on paper or whatever, is figuring out on what to do the induction, and often what should the induction hypothesis look like. So this is where creativity is involved, not just hacking. So it certainly seems that doing induction on L3 would not be very useful, because L3 is always going to be the second argument to append everywhere here, and the second argument to append is never investigated by the definition of append. It's only the first argument that it uses. So it's got to be either L1 or L2, and in this case, L1 is a good guess. So we do induction on L1. Once again, in the nil case, we don't need to bind anything. In the cons case, we bind the number at the head, we bind the rest of the list, and we bind a variable standing for the induction hypothesis. In the nil case, it's easy, as base cases often are. And in the cons case, we basically just use the induction hypothesis, and we're done. Okay, here is list reverse. And now, here is a proof that I think I won't bother going through with you, that actually, this is in some sense one of the first interesting theorems that we've had to prove. There were a couple of interesting theorems about numbers, but not too many interesting theorems yet. It's just been finger exercises. But this theorem is kind of interesting. It says if you, it tells you a relation between the length function and the reverse function. Namely, reverse doesn't change length. Length is invariant under reverse. And the proof is pretty simple, except that you need a subsidiary lemma. So if we simply try to prove it directly, we get into a stuck state where the induction hypothesis just isn't quite enough. So what you need is, because reverse is defined in terms of append, you need a lemma relating length and append. And once you get to this point in the proof and notice why you're stuck, it's kind of obvious, and you say, okay, well, I could have realized that beforehand, but it doesn't matter because I can just back up and do it. So you state this and prove it. The proof is not hard. And then with that proof in hand, we can go back to the first one and get all the way through the proof. Okay, let's see. I'm going to skip over those and talk about options. So we've seen already an awkward situation with the list head operation, where when the list is empty, we have to provide a default argument. But the default argument is a number, and the thing that it's supposed to return anyway is also a number. So how do we distinguish between, as a user of the head function, how do we distinguish between the case where the list was empty and we got back a bogus number versus the list was non-empty and we got back its head? Same thing can happen with functions like nth. So nth is intended to extract the number at a certain index in a list of numbers. And here we haven't bothered with a default argument. We could, but we've written it in a different bad way, where it just returns some default. It returns 42 if the list doesn't have enough elements. And I think I don't need to convince you that this is bad. So what could we do that's good? Well, we should introduce, in most programming languages, the good thing to do would be raise an exception. In coq, we don't have exceptions, so instead we return a value that says it wasn't there. And the convention, which again coq inherits from ML, is a type called option. In Haskell, it's called maybe. And it has constructors some and none. You may wonder, why are some and none capitalized here when all of the constructors, or most of the constructors so far, have not been capitalized? There really isn't any rhyme or reason to what gets capitalized and what doesn't get capitalized in coq. And the reason is that because coq has such a powerful type system, we end up writing things at the type level that do computation, and things at the value level that take types as arguments, and things at the type level that takes values as arguments, and all of the kind of simple rules that you would think of to keep the layers distinct in other languages don't really apply here, because the layers are intentionally mixed up. So some people have conventions. There's a general convention that things with capital letters are either constructors or types. Types are generally written with capital letters, but not always. And so it's really just kind of a mess. But at the end of the day, it doesn't matter that much. Life goes on. Okay, so nat option is a type with two constructors. The none constructor doesn't take any arguments. It just says there's no data here. The sum constructor takes a nat as an argument. So it says there is data here, and here it is. And now we can write nth in a better way, returning a nat option instead of a nat. So in the nil case, we return none. And in the case where we haven't found it yet, where we haven't recursed far enough, we just make a recursive call. And in the case where we did find it, we return some. And then when we call nth error, we're going to need to pattern match on the result to find out whether the result it gave us back was a good one or not. And this is a good time to mention the fact that coq has an if syntax that can be used instead of pattern matching when the thing you're pattern matching on has exactly two constructors. But wait, we defined our own Booleans, so how does the built-in if know that which is true and which is false? The answer is if works on constructors with on data types with two constructors, and it considers that the first one represents true and the second one represents false. So the fact that TRUE gets us to the first branch of true is completely incidental. It's only the fact that it was the first constructor that we defined in the Boolean definition.
What if my constructors were not nullary?
I'm sorry, what if the constructors are not nullary? Excellent question. So you can apply it to, for example, numbers, I believe. And in that case, the extra information will just get thrown away. All right. Yes?
So is this like a macro for the match?
It's a macro for the match. It's just convenience. Okay, we can use that, everything we've defined so far, to do a little bit of programming and define a type that's going to be useful a lot later on, which is the type of identifiers. So this is a trick that's often played in OCaml and Haskell, where we define a new type with just one constructor, which takes just one argument. So you might think, why is that a useful thing to do? Because the members of that type are exactly isomorphic to the members of the original type. And that's exactly the point. So they are isomorphic, they're not the same as, and the type checker will not allow you to mix them. So every ID contains a number, but IDs are not numbers. And that means that, that if you accidentally write a function that wants an ID and pass it a number, you will get a complaint from the type checker. And that can often be a good thing. We will use them as we go along for things like, well, we will use something similar for the type of variables in programs that we represent as coq data structures. Okay, now, we already wrote an equality test for natural numbers, but as I just said, you can't mix the types. So if we want to test for equality of IDs, we're going to have to write our own definition of an equality test for IDs. Of course, it's easy to write using pattern matching. There it is. Now we can define a type of partial maps. So a partial map is basically a list. In Lisp or Scheme, we would call it an association list. So a partial map can be empty, or it can be a record containing an identifier that is a key, a number that key maps to, and a partial map, which is kind of the rest of the bindings. And then we can define an update function that takes a partial map, an identifier, and a value for that identifier, and adds a new record to the front of the partial map that you gave it, which will, if that identifier, if that key happened already to be bound, it will now be shadowed. We're not actually throwing it away, so this isn't the most efficient update function that you could imagine, but it is correct in terms of behavior. And we can write a lookup function called find that attempts to find a key in a partial map, returning, of course, an option because it may not be there. Okay, here's a question for you. Is this theorem true or false? And please raise your hand when you know the answer, or when you're sure that you're not sure. Okay, some hands going up. So I am for the moment asking for people just to indicate when they've thought about it enough. And now that that has happened, what is the answer? So who thinks they know?
It's true.
It is true. So if you update a map and then look up the very key that you just added to the map or shadowed in the map, what you will get back will be the value that you put in. What about this one? I'll just give you a second to think about it. Okay, who thinks they know?
This should be true as well, because the first step of executing find will simply be the cursor invocation.
Yeah, so this is true as well, I agree, because the hypothesis that x is not equal to y is telling us that the top invocation of find will discover that the front thing on the updated map is not what we're looking for, and then make a recursive call, which is just the right-hand side of the equality. So whatever that gives us will be what we get back. Okay, and that is the end, and it's coffee time.